Alright, so I don't know if more people have joined. Let me just check. Oh, sorry. Discord should be here. Yeah, alright. Sorry, just one sec. Let's see if more people are joining. Announcements. Okay. Yeah. Maybe. Okay. Maybe I'll just. All right. So last time we first we can review a little bit from last time. Although I think the content could be a little bit dense, but however, this is like a higher level overview of inner or dot product and cross product. So this overview last time would actually cover, I think, several lectures content. So even if you are confused or didn't completely digest the content, and that's okay because we're going to come back with these, okay? So still like higher level is that just remember inner product, the result is a scalar, and there are two definitions for inner product. One definition is the scalar component. Okay, so I can change color a little bit. So definition one. And so if you have like the points coordinates information or coordinate form of a vector, then you can so then this scalar component definition is definitely convenient to use, right? So for the component form, you just plug in the the component of the vector u, and then also plug in the component form, the information for vector v, right? And then you just do coordinate wise x1 times x2, and then plus y1 times y2, and then z1 times z2 as a scalar, okay? So, and then the last time I should say, this is like a projection, okay? So last time, if we also this is definition 2 of the two vectors u and v. So if we say last time fix a vector direction of u, and then we have another vector v that is of some angle theta with u, right? And we say what is this inner product u dot v is length of u times length of v and then times cosine theta, and the length of v actually times the cosine theta is actually just like the projection, right? Or if we have a v and then we are we take some information of how long of its shadow, right? And its shadow has a mathematical term. You will see this definition or this idea of thinking over and over again. This is actually the projection, right? So the second inner product actually is a geometric definition that tells you information about how long can v project to the direction of u, right? And also the last time we say why this second geometric definition could be quite useful is that when u is of length 1, and then think of when we want to construct a set of pairwise orthogonal basis vectors. And then we said that like why unit basis vectors are important, because unit basis vector, we don't need to care about the magnitude to calculate like times like a big uh, numerical value. So if we set like the first basis vector u as length 1, then it's convenient, right? It's just 1 as a number. And then in the process of finding the next basis vector, so if we have a v that's not parallel to u but with some angle to u, so that v is independent of u. Independent, we also talk about that, like we talk about linearly dependent, right? Linearly dependent is another vector can be written as linear combination, and in this way, and in this scenario is a linear multiple of u, right? But apparently v has an angle of u. V is not parallel to u, so v cannot be written as a multiple of u, right? So v is actually in this case linear independent of u, right? So this is our information. So v is linearly independent of u. Then v has, the last time we also talked about vector decomposition, right? So then it must have like first some component like a horizontal component Vx, which is parallel to u, right? Then Vx, we can, in this case, we can give it a professional name, which is a projection, right? So we can always, decompose a vector v in terms of Vx direction and Vy. And then in this Vx, we talk about it is actually just, using your sine, cosine knowledge, is just the length of V. So this is a length operator, right? The norm, right? So length of V times the cosine theta, right? This is the projection of V on U, and this is the Vx, which is part of the definition of U dot product or inner product with V, right? So then V minus this Vx, or V minus this norm V times cosine theta, left us a component Vy which is orthogonal to U, which could be quite useful in later when you go to university to construct orthogonal basis vector, right? So because V minus the norm V times cosine theta give us the Vy, which is orthogonal to U. So we obtain, in this way, we obtain a vector that is orthogonal to U. All right. So yeah. So again, how inner product in geometric definition is useful is that U times V is, so again, we're just plugging this definition, right? This definition here. So we just manually plug in, nothing complicated. So this is so this is U norm times V norm, and then times cosine theta, right? And then we just plug in the value of U, right? The value of U, because U, the norm U is 1, right? So that we can write down this as 1 times V times cosine theta, which is, so the inner product just becomes a projection, right? So give us information about projection of like the second vector or whatever vector you're interested in. You just do inner product, dot product, and then you can get information about its projection onto the vector direction that you want to start with, right? And then this u, because for convenience, I just give you the norm of u is 1. And then for your future construction, when you go to university, you can always use a unit vector. So if for example, u is not, so for example, if w is not 1, then just make w divide over its length, then this is a unit vector, right? So if you start with any vector that is length is not 1, you can always make it a unit vector by setting w over the norm of w. This is our unit vector, right? All right. Yeah, so this gives us a shadow or the projection, right, on u basis vector. And then vy, or the vy is orthogonal to u, right? So vy is just v minus this, right? And then in the direction, of u, okay? In the direction of u. So this is actually just v minus vx, right? So vx is so this is actually saying that vx is vx is the same direction of u, so that's why you indicate the direction, write u down, and then the length of this vector is a norm of v times cosine theta, right? Yeah, so just so orthogonal just means 90 degree, okay? Yeah, orthogonal just means 90 degree, okay? Yeah, so if you're confused, that's okay, because you're learning it later in university, right? And the last time we also talked about the cross product. So the cross product and then a higher level overview is just, this is like the result of a cross product is a vector, and specifically this is a vector that's orthogonal. Orthogonal means 90 degree, right? So orthogonal to both u and v, right? So that if you imagine, like, just see what we draw last time if you missed a class. So if u and v is like a flat surface, okay? Flat 2D surface stand by u and v, and then the normal vector is just the normal vector by definition is just a vector that's orthogonal to both u and v, right? In this case, you can also imagine the x, y, z coordinates, right? You imagine, oh, x, y. So if I just imagine two unit vectors on the xy plane, and then one unit basis vector of length 1 parallel to x-axis, and the other one parallel to the y-axis, and then the cross product will just be the similar to the z direction, right? So this is exactly similar to what we have here. So u, v, and n, okay? u, v, and n. All right. And then the last time we're saying that given like the component form of u and v, the cross product, the name is that the first component is cross the value of u1 v1, and then look at this u2 v2 and u3 v3, and then make it like a square like this, or namely determinant, if you know determinant. And then the cross product is exactly the first cross, like u2 times v3 here, and then minus this direction, u3 times v2, right? And then the same for the second component is that we cross the second line, okay? And then for the second component, we'll cross the delete the second column and then pick out the first columm and the third column here, and then do cross product. So cross product is u1 times v3 minus u3 times v1, okay? And then the third one, maybe that's what we missed it. The third one is I guess you can guess, right? Delete the third column. The third one becomes deleting the third column now, and then pick out the first and second column and put them together in a determinant form. And of course, it's a cross product, right? So cross product is so there's limited space, but this is the third component is, yeah, I guess you know, right? So this cross is, you know, u1 v2, and then this cross is minus u2 v1, right? Yeah. So or maybe I can okay, sorry, maybe I should shrink these here, okay? Yeah, summarizing like a vector with this component form of this definition, okay? All right, and then there is another definition for cross product, but this definition is not for its vector now. So this definition is for is length. Definition of length of cross product, right? So this is a definition of its length, because again, cross product is a vector, right? And then so if we say something like, if we write down something in terms of the norm of u times, this is the usual time, times the norm of v, and then then and then times sine theta, okay? Then times sine theta. So okay, so let's see. Let's see. Yeah. And then if you want to, if we want to write down similar definition as the similar form as a inner product, like using the norm of u and then the norm of v and then the sine theta, know that in inner product is cosine theta, right? And then here cos product is sine theta, so this is a scalar, right? So this is a scalar, but however we stressed that many times that cross product gave us the result of a vector, right? So in order for this to work, we always need to put down the norm operator for u cross product v, okay? And then we can write down the equal sign. Yeah. So what I mean is just the second definition is not for cross product vector itself, but for the norm of it, right? So this is the difference. Yeah. Sorry, a little bit like a typo here. A little typo here is that when I wrote down the last time, the projection or the shadow, actually this is a lens, okay? So we talked about last time we can decompose. We can for in physics or in other yeah. So if you imagine like v is or even velocity, we can always decompose v into direction in the the standard coordinate system, like the horizontal direction, which is vx. I call it the vx, right? And then the vertical direction, the vy, we can always decompose in this way, right? We can always decompose in this way. The vx and vy are the uh, two decomposition vectors in terms of the coordinate system, right? And then um, if I fix my starting vector u horizontally, and then so v is projection, the length on u, so meaning that this length, right? This length is the norm of v times cosine v, right? This is a length, which means this is a scalar, right? And then in terms of written down vx, what is vx? If we only know starting with the vector u, that this is our only information u, is that for vector we always just have a magnitude and then the direction, right? And then the direction is, you know, so this is a little bit complicated. The direction is u direction, but I make it a unit vector. Unit vector just means length 1, right? So u over the length of u. So this is vector vx, right? But whatever, like uh this this here, you don't need to worry about too much, right? So but you only need to know that this is the length, right? So this part is a length. So v norm cosine theta, this is the length of this vector uh, projection on u, right? So this is the length of or the projection, length of projection of v on u. Okay, yeah. Yeah. So again, in this inner product definition, we only get information about scalars, about numbers, right? Without a vector. We didn't get like a vector direction information from inner product, right? So this, because norm, cosine, these are all scalars, right? Right. So yeah, just to make it clear here, right? So Vx is, the length of Vx is actually exactly the norm of V times cosine theta, and then the vector direction of Vx is actually the same direction with u, but the length of u we don't know, so the length of vector u and then over is norm, right? So that's why we give an example of u being the unit vector of length 1, so that I just let you see, oh, the inner product definition here is quite convenient now, because when the length of u is 1, so then uv inner product, so this is a usual formula, and then after we plug in the length of u, we get exactly the norm of v times cosine theta. So this is exactly the length of the projection, right? So this exactly give us the length. Okay. All right. um all right, so we'll probably should start with some more basic ones and then proceed from there. Okay. Yeah, but if you just keep in mind inner product, the difference of inner product and inner product and cross product, and keep in mind, have a bigger picture, and then we can go like much easier, is like much easier, faster than for us, right? So velocity is a vector measurement. Yeah, we know velocity. And So relative velocity of an object. Yeah. So this relative velocity you can understand as, so if we have a like a car one or car A, okay, and then if I have a car B, and then they're both driving. Just imagine like you're racing, have a car racing, two cars, on the road, and then maybe one car is faster than the other, and then let's assume that the car B is faster than the car A, okay, and then of course they both individually have a velocity VA and VB, but uh, what do we see if we sit on car B and then watching car A is that uh, you know how fast if we do we feel when we watch the car A on car B, that's the relative velocity that we perceive is VB minus VA, right? So this is just an example, like how if you are on car B, like how fast do you see car A is this relative, right? Um, yeah, so I think this is okay. And the car, let's see, the car is traveling, and so I don't know if this is interesting. And a motorcycle is traveling at this speed, and the truck and the SUV. Find the relative velocity of the car relative to blah blah blah. It just using the minus, right? So let's say the car is this, and then let's see an SUV. Okay, let's say an SUV because it's also 100 kilometers. This one. So we let's say car and SUV is just going to be 100 kilometers per hour. Okay, per hour east, right? The direction is different. And then minus 100 kilometers per hour southwest. Okay, so let's draw this. Like this is the north, the east, southwest. Okay, southwest is probably like this, right? So one vector direction is this, and then the other one going north is this, right? And then and then we just do. Oh, sorry. This is like what I wrote down here. It just So this is the magnitude, right? How long is a vector, and this give us a direction, right? And I still think that it's east should be going here, right? So east should be going here, but somehow I still think it's quite convenient to write down as the component form. I'll just assume that this is the x direction and this is the y direction. So I think it's easier to calculate in this way. And then x direction is just 100. So east 100, 0, right? 0 on the positive y direction, and then minus southwest, and then x and y. What is this x and y? Is going to be, so 100 times cosine 45 negative, right? Because it's a negative direction of x, and then also this. Yeah, I think you guys are fine. And then cosine 45, this is square root 2 over 2, okay? And then you just do calculation, it's fine. Yeah, I think it's okay. And then let's see, boat velocity relative to the ground is a vector sum between the boat velocity relative to the water and sorry, and the water velocity relative to the ground. Yeah, I think this is quite interesting, right? So yeah, so this could be like an application, a classic application problem. If you have, on the ground, and then this is a river, so this application problem could happen, right? So this is some river, and then you have the boat, right? Yeah. Sorry. Let's see. Um, yeah, the boat is some uh, of some velocity. Let's say the v boat, right? So we can further, you know, uh, decompose it. So vw means velocity, you know, sorry, this is a velocity of the boat relative to the water. So water have vw, okay? So, and then I can just expand this as vb minus, so know that it's a vector, right? So vb minus vw, and then plus, you know, and then v water relative to the ground is actually, I can just you again, just using our formula on the top, right? So this just becomes v w minus v ground, right? After we decompose it, and then we can say, we can observe that this is actually just vb minus vw, and then when we plus a vwg, we plus a vw again, right? So minus 1 plus 1 is cancelled actually. But however, even if you cancel, it's like different meaning, right? Give us different meaning. The top one gave us like the meaning of how we going to understand the v boat relative to the ground. But actually, after we expand it, this is actually just simplifying to the vbg is actually just v boat minus the vg, right? So which is consistent with our top definition, just the boat, v boat minus the v ground, and of course, the the v ground should be 0, right? The v ground should uh usually be 0, but let me not say 0 for now. But who knows if it saying, oh, the ground is of, like, the earth is moving of some velocity, we don't know. And then this is a plane velocity. Yeah, let's see. The plane velocity relative to the ground is the sum between the plane velocity relative to the air. So this should be here, right? Change it a little bit. And the air velocity relative to the ground, okay? Yeah, I think this is the same. Okay, let's see. Yeah, maybe we can do an example, but this should be similar, I think, right? Boat and plane. So let's say a river eastward, flows eastward. So do this application problem, I think, is always somehow useful to draw some pictures in order to illustrate the procedure, right? The process. So flows east, and then I'll just say v water, okay? vw is v water, is 4 meter, blah blah. Yeah, so water flows, and the motor has okay, I'll just say a direction here, right? So you can also draw a picture in your own pad or something, just to feel, just to perceive the story, right? And then motor boats had downstream the river between the two towns, which are 50 meters apart along the south bank of the river. Okay, so so this is like some information. Okay, so first we have a motorboat. I'll just draw this, has downstream. Okay, downstream, I'll just assume that this here, okay, has downstream. Wait, downstream. I mean downstream is, sorry. It may be. going down here. Maybe this is what it means downstream. Okay, so if you have different understanding, just let me know, right? But what I understand is that the river flows towards the east. Of course, if the river is flowing in this direction, and then the downstream would be the opposite direction that the river flows. The downstream is the opposite direction that the water flows, right? So yeah, I think let's see this right now. And then between two towns which are 50 kilometers apart along the south bank. So south, we can also have a direction like a south is going down this way. It's the south bank, right? See the language? Along the south bank of the river. So bank is here. So this is the south bank, right? And then the two towns 15 meters apart, right? So let's say this is town A, right? And then town B, but I don't know which one is like of which position. Let's see. If the motor speed in still okay, if the motorboat speed in still water is 12 meters per second. Yeah. Yeah, so this is important that it's you know the motor speed without subtracting the water. Like in still water, it just if the water doesn't move, like as if the motor is driving on the ground, and then it's just v 12, right? So I'll just say like this v boat is I don't know, okay, maybe negative 12 because this is driving downstream, right? Downstream I think must be the different direction as the water flow. So this here, so sorry, this is town A and town B. Okay, and then the speed of the motor boat relative to the ground when traveling downstream. Okay, think about this one. I think this is direct from the definition, right? Isn't it? Okay, to the speed of the boat. Okay, to the speed of the boat relative to the ground when traveling downstream. Yeah, I think the definition is a little bit is a little bit messy here, right? The definition here. Okay, let's see what's going on here. Yeah. So if we are plugging in the definition, the speed of the boat relative to the ground, okay, okay, let's see, the speed of the boat relative to the boat velocity relative to the water. Yeah, so the boat sorry, the boat velocity relative to the water is I think it's a matter of we need to understand what is this boat. So boat speed velocity relative to the water means, right? So okay, so maybe I should like take back off the definition, because the relative velocity of an object BA is VB minus VA, right? It's VB minus VA. Um, I think we can still we can still write a definition here like VB minus VW. This always hold true, right? By definition of VW. But however, so this is how we understand the boat relative to the water. And then this sentence, look at this sentence. So if the boat speed in still water is 12 meter per, so I shouldn't simply draw in this way like VB, right? So how to understand this velocity? So boat speed in still water. So is this VB or VBW, right? So 12 meter and downstream, right? Downstream, I'll just say minus, okay? So is this the VB, the V boat, or the VBW, right? So this probably should be the V, sorry, VBW, right? Yeah, because the boat speed in still water, so relative to the still water. Okay, I'll just write down the definition like this. So so our relative boat velocity relative to water is negative 12 meters per second, right? Uh, and then, I think then we can just plug in the formula now, okay? And then VBG is VBW plus VWG, okay? Then VWG, the water relative to the ground. I think this one is easier to understand. It's just how fast the water flow, right? So, and then the second entry is just plus 4 meters per second, right? Because I assume like this is the eastward, and this is like the x positive direction, like 4 meter 4 meter per second, and then downstream like negative 12 meter per second. So and then but now so I have this negative sign and the speed relative to the ground when traveling downstream. So the negative sign is just indicating the direction, right? But the direction is already specified as downstream, so the speed is just traveling uh, 8 meters per second downstream. I think that's fine, right? Yeah. And okay, let's see this plane. I think let's see how it's different, right? So the plane is scheduled to travel from airport A to airport B. So with 60 degree. Okay. Um. Then this really tests me about the definition of vectors. Okay. Actually, I forgot that this. What does this symbol mean here? Even like 60 degree. Like, should I say this is 60 degree, or this should be 60 degree? You can correct me if I'm wrong. Okay. Um. It didn't even specify the north or any. Okay, let's keep reading. The speed of the plane relative relative to the air is plane relative to the air. I think this is just VPA. We can directly plug in here, right? So plane relative to the ground is plane relative to the air, and also plus the air to the VAG is air relative to the ground, and then this is the wind, right? The strong wind of 100 kilometer per hour, and then this is a V air ground, okay? V air ground, and blowing eastward, okay? All right. So yeah, so I don't really understand this notation here, like 60-degree, because it didn't give me like a north direction or some axis, right? So I'll just assume that this is 60-degree, but you can definitely correct me like later if you know uh if you think I drew it wrong, okay? And then we eastward here we have the VAG, right? 100, and then the plan is we should give like a here give us a magnitude, but we should always give it a direction from A to B. Give it a direction here, this VPA, right? And so draw a diagram to illustrate the situation, and then yeah, and then let's just directly plug in, right? So PG, this is PG means PG means plane velocity relative to the ground, right? So P here and G here, plane ground, PG. So yeah, so this is just nothing but plug in, right? Just plug in the definition here. So if you can remember this, so V P A plus V. Okay, so this is exactly like what we studied before, the vector summation, right? So so look at here. So plane, air, and then air, ground, right? So this is exactly when we studied before, summing the vector together, like starting point, middle point, travel point, and then the middle point, and then the end point, right? So this is like our object. This is we study the velocity of plane relative to the ground, but then at the same time is it have like an intermediate uh it have an intermediate object, right? Intermediate object of of the air, right? So plane relative to air relative to the to G. Yeah. So if we decompose the vector as a summation of two other vectors, we just have something like some intermediate object to to decompose it. Yeah. So that's the idea. Also, like the boat relative to the ground, BG, and then we just like insert an intermediate comparing object like W. So BWWG, right? So you only need to so how to say, like the point is that if you were to remember this definition, you only need to understand. So right, just understand what is the intermediate object that we are comparing to, right? So this intermediate is water, right? So let me see. So intermediate water, and then this different. The only difference here is that oh sorry, the intermediate is the air, right? Right. Yeah. And now we just plug in our definition. I think well, if you really want to calculate it, you can just plug in the component form, okay? If you really want to calculate it. But I think yeah, but I think we can skip the calculation for now. Okay. And then okay. Oh, okay, okay. So it's really going like downward. Each of the question is going downward. Okay, so let's take a break, and I will upload this to Google Classroom so that you can, yeah, you can take it as a reference, okay? Because the next question is the next page. You couldn't see the description, okay? So I'll upload it now and then take a 5-minute break. Okay, let's see, 7.2. Okay, 7.2. And uh let's see here. Yeah, so now you can download 7.2 if you want. Okay. Yeah, so I don't know if everyone can open Discord. Yeah, I think it should be fine, right? Okay. Um, all right, so yeah, so I don't know if you can download that, but let's keep going with our question. So yeah, so the next few question is like going downward here, right? Uh, yeah, so let's see. So I think these two questions are, similar, right? So just identify the relative, description. So this VBW here on example 3, uh, and then just identify the relative velocity and then the direction, right? And then for question B, saying that, oh, the time required to cover the distance between the town downstream, right? So it's meaning that, so if our boat is driving downstream, like going this way, and then the time that it can travel maybe from town B to town A, or the distance between them, right? And the distance between them are 50 kilometers away, right? You have AB object, we have 50 kilometers away. Okay. Yeah, I think then this is just using the so the time is usually it just our distance over our speed, right? Or the norm uh, of the the magnitude of velocity, okay? Because velocity usually give us the direction, right? But if we were to calculate, the scalar or the time, we just use this norm, okay? So here the distance is 50, the same unit, kilometers per kilometers, okay? And then the speed is, oh sorry, this is 8. Oh, the unit are different. Okay, so this is, yeah, so this is tricky. A little bit, a little bit sneaky here, that they put like a distance of kilometers, so 50 times 1,000 meters, right? So don't so if you do this question, don't forget to convert the unit. And also the speed is, I'll just say 8 meters per uh 8 meters per second, okay? 8 meter per second. All right, and then you get like 50,000, right? 50,000 over 8 seconds, and then you can convert it to hours. So this is just a matter of calculation, right? So the speed of the boat relative to the ground when traveling upstream. Yeah, this is like another picture now, right? So boat uh traveling this way, and also water is also this way, right? And we see that we know the boat is v water, right? So again, we read this description of the motorboat speed. uh so if the motorboat speeds in still water, so yeah, so I think this should be the the motorboat speed relative to the water. So VBW, right? We talked about that. Uh, so VDW is 12 plus 12 now, and V water, I'll just say VWG, right? So water flow speed is just water relative to the ground is 4. So this is so I'll just write down the formula again. So VPG is equal to VPW plus VWG, right? So I'll just do it. So 12 plus 4, right? The same direction. So this upstream means the same direction as the water flow, right? And then the and then the time required to cover this distance between towns upstream. So I'll just draw like A and B town, still 50 kilometers away, and then the time to cover this, yeah. So it's the same, right? Distance over the speed, right? But the only thing like the speed is different now. So 50,000 over what? Over 16, right? Over 16. Okay. And again, yeah, sorry, the order, like I mistaken the order. Yeah, let's see. It's 4. Question 4, okay. Again, is the speed of plane, VPA, plane speed relative to the air, and then VAG, it says airspeed relative to the ground. But airspeed relative to the ground here is just the wind, right? So strong wind is V airspeed relative to the ground, right? Yeah, this is funny. Okay. Um. Okay. Oh. So, in question B is saying exactly in what direction should the pilot head the plane? Okay, interesting. Uh, so the plane schedule to travel from point A to point B. Uh, and speed of the plane to the air and the strong wind. And see what direction should the pilot head the plane. Okay, yeah, yeah. This is an interesting question because okay, I think okay. So sorry. What we draw here, we directly draw the VPA in this direction, but actually uh not not quite that simple, right? Yeah, so we made a mistake when we first drew like the first diagram that we drew. AB like this is from here to this direction, right? But VPA not necessarily, because yeah, this is a good this is actually a good question to practice, because the resultant vector, okay, I'm using the word resultant. The resultant vector is actually, you know, heading not necessarily. Um, so the resultant vector is, it'll change direction, right? So this is the V air ground, right? Or the V or the V wind, right? Or the V wind. Okay. And then I know that I need to travel from A to B. I need to travel from point A to point B, right? I need to travel from A to B, and so the result, so the result direction that we need to go is actually this direction. Like the result we need to travel, right? Um, so, but however, in order to travel in this way, because it's affected by the wind, you need to originally travel the direction have somewhere toward here, such that in the result you can, after the wind blowing east, you can, the result is going this way, right? So the plane, uh relative to the air, like you should go somewhere like this, right? So that, when VPA plus VAG air to the ground, which is just the wind, right? Just the wind, such that this direction V is from A to B. So this is actually the VPG. Okay, VPG is just our just from A to B direction, right? This is from A to B direction. Uh, all right, yeah. So yeah, so the VPA, the VPA vector, like it should have this, right? So VPA equal to VPG this direction, and then minus the VAG, right? And okay, and then now we just do some uh, triangle, okay? And now we just draw some triangle, and then to the east, this side, this velocity is of, the wind is 100, so I'll just simply write down 100, okay? The wind, and then I'll do like a parallel VPA. I'll draw like a parallel. I'll draw like a parallel. Like imagine, assume that this is the VPA direction, and then I draw a parallel line here. So, and then the resultant triangle should be this, right? The resultant triangle, that this should have a, let's say, the resultant triangle, this should have a 60, sorry, it should have a 60 degree, right? Right, should have a 60 degree. And that, let's see, right? So it should look like this. Oh, sorry. Maybe I'll draw this longer, because the plane, this direction, this speed is bigger, right? Like 600 something, 600 something, right? So I'm just drawing like the side of geometry in order to imitate this, and then this side, 100, okay? And then I'll draw like a parallelogram here, here, here. All right, all right. And then the resultant, of course, the diagonal of this parallelogram, because we want to have the resultant direction is from A to B. So the diagonal should be A to B, right? Yeah, let's see. Let's see that, like this should be our 60 degree, right? So this should be our 60 degree, and then uh, uh, yeah, I think I really got bumped out by this somehow, right? So this is like, it is obvious to calculate this. Okay, 60 degree, and this is like 600. let's see if this is obvious to uh, okay, if this is obvious to calculate this angle, right? Yeah, I think somehow I got bumped out by this. So if we have a yeah, if you have a triangle, if you know two sides here and one side here, and then the angle, like, can we know the other angle, right? And then that answers our question, like which direction it could head. Okay. Yeah, I'm actually not so sure about this one. Mm, yeah, I think it requires some calculation, right? It requires some calculation in order to calculate this angle. Yeah. I don't think it's that obvious to me. Uh, oh, sorry. The plane. Oh, sorry. I think I should draw. Sorry, this plane speed is like 300. Plane to the air is 300, right? So I should draw like 300 here. Okay, but still, is I don't think this is too obvious. Uh, yeah, it just requires some work to calculate, right? And this is 100, this is 300, and then the resultant velocity should be here, right? The 60 degree, yeah, yeah. Still, I don't think is that easy to see the direction. So, yeah, I think if I think about something, I'll come back to this. Okay. Uh, let's see if I missed something. Yeah, sorry, this should be the 300, right? So I keep saying, sorry, I keep saying 600, so this should be like the 300, okay? 300 something per hour. So this is 100 air ground, sorry, 100. Okay, sorry. But this direction we don't know, right? This direction, like a bigger bracket for this. Uh, yeah, it's just like to say, so for them, this one, this is 3, and 1, 3. Okay. Um, yeah, yeah. Sorry, I'll skip this one. I don't. Yeah, I don't have like a obvious, but the resultant should be like here, right? Mm, yeah, I think it just uh requires some careful calculation. Uh, yeah, we can maybe assign the x y variables. so that this V, so let's see, VPA is XY variable, and then the V wind is 100, 0, right? And then the summing up of these two, let's see. So VPA plus V wind is, see, so it's actually 100 plus X or minus X. Oh no, okay, so plus X, okay, and then Y. So this is our result. Okay, so maybe it's not that bad. Let's see. Okay, so maybe it's not that bad. And this is the resultant vector toward this way, right? And this is our V, I just say VAB, right? Because we want the resultant velocity vector traveling from A to B, okay? And then we know that this is 60 degree. You know, if I understand, like AB like 0, 60 degree, if it means that like 60 degree drawing this, right? And so we know that this vector is this. Okay, so this is maybe not that bad, okay, but it definitely requires some calculation. And then we can, using that, like tangent 60, okay, so I can move it upward a little bit, and we can use that, the tangent 60, right? Tangent 60 is y over, yeah, I think maybe you guys are smarter and think of something easier to calculate, okay? So VAB, what I mean is here, VAB, and then we know it's coordinate, and then this is 60, right? So tangent 60 is the y over the x, right? These are tangent 60, and we also know, so this is the first formula, and then we also know that we also know how to say, we also know the magnitude of VPA, right? So square root of x squared plus y squared is going to be 300, right? Because the plane relative to the area is 300, right? Yeah. So I still think, okay. So I still think it's not that obvious to me. Okay. Yeah, but it's we can definitely do the calculation, okay? So I'll erase these ones because these are just some drawings to clarify thinking, but without too much information, so I just erase them here, and then I'll put it here. And the second formula is second formula is this is equal to square root of xy, okay? Square root of, I'll clean it out, and then square root of x squared plus y squared is going to be 300. And then what is our xy again by definition? Because the direction of VPA is unknown, so I just set up the VPA as xy, and the VW, the V wind, is 100, 0. Okay, yeah, so then this we can solve for x and y, right? Right? Yeah, okay. Because yeah, because our 60-degree tangent, you see, so it so if we draw like using unit, so sine, we'd always know sine 30 degree is 1/2. So 1/2, and then this is a scale, the unit length, right? And then if I draw this side, then it's square root of 3. So 1 square root of 3, 2, right? And then this tangent 60 degree here, this tangent 60 degree here is just square root of 3, right? And then we can calculate these definitely, right? Yeah, yeah. Okay, okay. I think we can I can go to some like other more other like type of question. Let's see. Okay, so this is uh okay, so this is again like a river and water flows. Let's see. So river is 800 meters wide and flows eastwards. And again, like, okay, and then eastward, we know that this is a V water. So this is a V water relative to the ground, okay? And then Peter is driving a motorboat heading always perpendicular to the current. Okay, so it's heading perpendicular to the current, and the speed of the water is in the speed in still water is 12 meter per second. Yeah, so this is again like we just identify, we draw the diagram, identify its velocity direction, and then do summation of velocity, right? So draw a diagram to illustrate the situation, the eastward, and then we can have so VWG, right? And then so Peter is always heading perpendicular to the current, so we're assuming Peter is always, so V Peter, okay? So V Peter, we say that is always perpendicular to the current, right? And yeah, so we draw Peter like vertical, this velocity, right? And V Peter is actually just a V motorcycle relative to the so motorboat, so the boat relative to the water, right? So and then the speed of the boat in still water is 20 meter per second, so velocity boat relative to water is this, right? So this is a V boat relative to water, and then this is 20. All right, so this is 10, this is 20. Okay, and then what is the speed of the boat relative to the ground? Okay, all right, so speed of the boat relative to the ground, we do nothing but just plug in our formula, right? So this is nothing fancy, I guess, nothing new. BG, right? And then we just manually the formula right here. And of course we want to do coordinate form, just yeah, I think easier for calculation, right? So that's why in previous calculation it requires some, more work for calculation, but I still just assume that because it's asking the direction. Direction is like if we have a coordinate system, if we write down the vector component form, right, with a coordinate system, and then we can just it's a way also to represent the direction information, right? So yeah, so I think it's handy now to write down this vector as component form because it's vertical. The boat of Peter vertical. So I'll just say this is 0, 20, and then plus our water to the ground is 10. I'll just east positive direction of x, 10, 0. I'll just write down like this, right? And then how long does it take to cross the river? Okay. How long does it take to cross the river? Yeah, this is a good question, right? Uh, so yeah, so so our perpendicular, you know, so the perpendicular, um, so if it's starting to head out perpendicular to the bank, and this is the water, and then the resultant velocity is heading this way, right? The the resultant velocity is also heading this way, right? V resultant also heading this way, right? But however, like V resultant is is V resultant is it's just our V relative to the ground, right? This is our VBG, right? So I mean, if you want to, you can uh, okay. Okay, yeah. So VBG is of this directions. So if you draw the vector, uh, this is the x. Maybe this is the x coordinate vector. So so this is Vx, right? Vx direction. I'll draw this is a 10 here, and then the Vy direction. I'll draw it. This is a 20 here. Draw this a 20 here, right? Um, and then it depends on like how you want to solve it, but because the vertical direction, the vertical distance is always 800, right? So you can either say like it's actually traveling this way with an angle, and then you can calculate like this distance over this speed, or the vertical velocity, it always is just a Vy, right? And or you can directly using the vertical distance 800. So vertical distance is still like 800, and then using the Vy, the vertical speed, right? So one way is that you identify Peter like is actually heading toward this way, and then we calculate this angle using some sine cosine, right? Uh, we can definitely calculate this because this is because if this is 800, and then using sine cosine, because we know that it's 20 over 10 here, right? Um, so this is 400 here, and then we can calculate this distance, blue distance, and then divide it by the resultant resultant velocity here, right? Resultant velocity is just the boat relative to the ground. Okay, you can either calculate this way, or because we just know like how long it crossed the river, or you can use the vertical distance is 800 meters, and using the vertical speed is a vertical velocity. Okay, or vertical speed. Okay, yeah, because velocity have direction, speed is just our magnitude that we use, but that we need. So this is 800 over 20. Okay, so 40, say 40 seconds. Okay, that's a little bit too fast, isn't it? Okay, and then how much downstream does Peter reach the opposite bank? Okay, um, yeah, yeah, sorry. So downstream, okay, so maybe I think my description was so flow water in this way. So maybe my description has a problem, so sorry. Yeah, I think I made several typo here. Like downstream is going this way, right? Downstream is going this way. All right. And then how much does Peter reach the opposite bank? But so V B G. So after Peter is traveling in this direction here, right? So Peter here, and then the destination. But however, like the vertical Vy doesn't contribute to the distance, the horizontal distance, right? So will contribute to the horizontal distance is just a water flow here. This is Vy, right? Vx, right? So you can see that our Vx is just a V water relative to the ground, right? And then how much the speed to reach the opposite bank is just the distance. It's just the distance x, right? So this is our uh, distance x, right? So we can also decompose this vector, how much it travel along the x coordinate. So distance x is time multiplied the velocity, right? The time we calculate is 40 seconds, and times the speed. So speed, Vx, right? Yeah, so 40 times Vx is 10 meter per second, right? Yeah, so it's 10 meter per second. So 400, okay? 400 meters. So yeah, from I think the geometry, we can also deduce this, right? And let's see, okay, so swimming. Okay, but swimming is similar to the boat and the water, right? So Jen can swim 5 meters in still water. So this is our V boat water. Okay, sorry. And she wished to swim across the river 200-meter wide to a point directly opposite from where she's standing. Okay, so this is interesting because it should so the resultant velocity should be going, y to directly opposite from where she's standing. So if she's standing here, Jen, and the destination should be directly opposite, like, and then so the velocity resultant should be vertical, right? The resultant velocity should be vertical, and then the resultant velocity is just so sorry, it flows westward, and then we can draw like a W water ground in this direction, and she's standing on south bank. Yeah, we will draw it correct. We're standing on south bank, and then if the resulting velocity is going upward, so Jen should really head the v Jen, right? V Jen is just V are both relative to the water, right? Sorry for calling Jen the boat all the time. So the V Jen should be this orange, right? So V Jen is our V boat relative to the water, okay? Should be this orange direction, such only heading toward the east a little bit, right? And then such that we want our resultant is going upward. So this what is the speed of Jen relative to the ground? Okay. So Jen can swim. Yeah. Yeah. So yeah. So we can draw like a we can draw a triangle here, right? So this, and then this is V water ground, and then the result should be, yeah. So this is like quite obvious or easier to calculate because the resulting is perpendicular, right? And then this is 4 and this is 5, and it should connect to the V resultant as a triangle, so that this is orthogonal angle 90 degrees, so that this should be like 3, right? Yeah. And so what is the speed of Jen relative to the ground? Relative to the ground is just a V resultant, right? So so that V speed of Jen relative to the ground is exactly the same as speed of boat relative to the ground, right? So VBG is still our VBW plus VWG, right? And our VBW is the boat in water, Jen in water is VGen is 5, right? So VGen, right? And plus our V water, okay, V water G. But what we summing up here, this is the velocity vectors, right? But however, in A, we already, analyze the triangle that is triangle or the geometry for this question, right? Because in order for the resultant to be vertical, like it's a triangle should look like this, right? So this is 4 and this is 5, right? And then the resultant is going upward, and then we already by the Pythagorean theorem, so square root of 5 square minus, so this should be minus, right? Minus 4 square is 3, 3, right? So this should be 3. So the speed is the magnitude of the velocity, so that this is 3, right? Yeah, so again, which direction must Jen head? We just calculate. So this is 5, 4, 3, and we just calculate this theta. We can say is arc cosine 4/5, okay? Or cosine inverse. How long does it take to cross the river because of V resultant? So V resultant is 3 meters per second and north, right? North. So this is our V resultant, and V resultant is vertical, right, to the bank, and um, so that going vertical and across the roof 200 meter. So the time should be, using our distance is, so this is 3 meter per second, and then the vertical distance is 200 meters. So this should be obvious to us, right? So 200 meter over 3 meter per second, right? Yeah. Yeah, I think this should be like not, yeah, you guys are probably like smarter than me. So yeah, I believe that you guys are smarter than me. Yeah, so wait a second. I will load the next PDF vector. Okay. All right. Sorry. So let's see. Let's see if I can open this in my drive. Not sure if this is this one here. All right. Oh, this is 2 here, 7.2 here. And yeah, and this should be yeah, and this should be not hard for us. Using this, right? All right, so dot product finally, because I think those applications are, are just how to say, like stories that we need to, if you're just like um familiar with the terminology, like both water, like there's an intermediate object, both water ground, or both or plain air ground, and then you're fine, right? It's just a way of storytelling, but really the math knowledge is, for this section, is, for this unit, is dot product or cross product, right? And we already talked about, the overview. So definition, like dot product of two geometric vectors a and b. Between them, like the scalar form is this, right? So we already talked about, if we a and b have a angle theta, and then the dot or inner product, right? Inner product. In university, you will learn this as the inner product, okay? And it's norm A norm B times cosine theta, so this shouldn't be surprising now. Okay, so find U, inner product, we will, yeah, it's just nothing but plugging in our formula, right? So yeah, so I didn't do much, but just to copy again, right? So, and cosine 140. So the scalar dot product could be negative if our cosine is negative, okay? And then okay, so find the angle between two unit vectors with a dot product. Yeah, so in this way, because this formula contains a cosine theta information for the theta, so that we can know using inner product to calculate the theta, right? So so the angle between two unit vectors with a dot product equal to this, right? So first thing first, so if you know the dot product result is this. So if you know u inner product v is 1 over square root 2, okay? Yeah, so provided if you know this. And the last time I think we talked about if you encounter this kind of problem, so how do you easy to know a inner product? It just, if you know the coordinate or the component form, the coordinates of two vectors, you can directly calculate the inner product, right? Yeah. And then now it tells you it's a unit vector, right? So unit vector means exactly that the norm of u is equal to the norm of v is equal to 1, right? So now we can just calculate this, right? So this is a formula we probably want to apply. So cosine theta, we still use the same formula, right? So cosine theta is just the inner product. So or just look at this formula over here, right? Cosine theta is the inner product u v and then divided by its length, right? So this u multiply with the length of v, right? And so now it tells you it's two unit vectors. Unit vector means length is 1, so this is 1 times 1, and then inner product is this, right? All right. All right, and then okay, so properties of dot product. So of course this is scalar, and then if A were to go orthogonal to B, and then A inner product B is equal to 0. Yeah, and then this is exactly because A inner product with B is the norm of A, and then times the norm of B, and then times the cosine 90 degree, right? And then cosine 90 degree is so norm A times norm B and then times 0, right? Because cosine 90 degree is 0. So that's why when A orthogonal to B, the angle between A and B is 90 degrees, inner product 0, right? So and or is saying if the inner product A and B is 0, is either length of A 0, length of B 0, or A orthogonal to B. Yeah, I think if you understand this, it's fine. You don't need to remember every conclusion, right? And also if their angle is if inner product is positive, means that cosine theta is positive, and then of course the theta is between 0 and 90. And then again, you don't need to remember this conclusion, just understand it, right? And then again, it's saying that, oh, if theta is between 90 or 180, and then cosine theta is negative, so inner product is negative. Yeah, I don't think you need to just understand it, right? And then if they are A and B are parallel and the same direction, right? So it draw like a direction arrow here, like going up, right? And then cosine, so and then the theta between A and B is 0, so cosine theta is 1, so A inner product B is A times B, right? And also parallel but different direction, up and down, theta is 180, cosine theta is negative 1, so inner product AB is negative norm A times norm B. I think it's fine here. And then this is actually just also plugging in. You don't have to, just don't you don't need to worry about remembering things. It's just quite direct plugging, you're fine, right? Yeah, and then commutative means you can switch them. Distributive, break the bracket is fine. Scalar is fine. Scalar times k is fine. And then a inner product 0 is 0. Uh, yeah, I think, okay. Yeah, and this is just norm square. Okay, so maybe you can get used to this thing, this way of thinking. When we say norm square, you can also, another way to write it is norm square. Another way to write it is inner product. Write it in inner product is a vector plus b vector and inner product a vector plus b vector, right? Yeah, so norm square is equal to this. It just, yeah, it just so for example, as a vector, a vector inner product with a vector. Yeah, so what happened if you just plug in the inner product formula is the norm of a multiply with the norm of a. Sorry, there's not enough room, but cosine theta, right? Cosine theta is, so theta, like a vector, the angle with itself is 0, right? So with cosine 0, so this just becomes a times a, right? So or a norm square, right? So that's why, yeah, so that's why we write down like this. So norm square, so norm a plus b square is a plus b inner product a plus b, right? Yeah, and in the same way we also write the other ones. So okay, so they say to prove this each relation, we can just break the bracket. So I'll just say break bracket and then expand it. You can see, right? So a inner product with a, and then plus, you know, ab ba, right? So 2ab when you break the bracket, and then plus b vector and b, okay? Yeah, plus b vector and b, okay? And then of course a inner product with itself is just norm a square, and then plus 2 this, and then plus norm b, okay? All right, and then what about this one? This one is the same, right? So we just using a norm square. Okay, it's a norm square like a minus b inner product with a. So norm square is inner product with itself, right? So whenever you see this norm square, you can write it down as the inner product with itself, and then just expand, okay? Yeah, so, and this is also expand, okay? This is also expand is a dot a minus b in dot product with itself, okay? So this is nothing fancy. So if the vectors, if the vectors are perpendicular to each other, and find the angle. So if the vectors are perpendicular to each other, we're just using this perpendicular definition, so that if one of them is 2a plus b here, perpendicular, also perpendicular just means orthogonal or 90-degree, right? So this is what it means. And then we translate into math language, it's just 2a plus b inner product, right, is 0. And then we can get a relation, right? And get a relation of A and B, right? Get relation for A inner product with B, and then use B. The normal B is 0 to normal A, and then we can have we can use a cosine theta, apply the formula that cosine theta is inner product of A and B, inner product A and B, and then over the normal A times the normal B. Okay, yeah, I think if you follow this through, this should be quite easy to calculate, and then you should be fine, right? Yeah, so you can calculate this if you want to. Let's see, 4. Okay, let's see 4. Here. Okay, 4. I wrote down a lot for 4, but okay, we wrote down. Okay, we wrote down a lot for 4, but we just keep going, right? Yeah, so dot product for standard unit vectors, you don't need to worry about this notation. It's nothing but in the x coordinate. So in the x coordinate, y coordinate, and z coordinate, I said that in this coordinate system, unit vector, then we don't need to worry about the length, right? So I, J, K, you see this order is writing down I first, J second, and then K last one, right? So in x coordinate system, x direction, the unit vector is I, and then x, y, z, I, J, K, right? The order of the English letters, right? So you can just so x, y, z, and then I, J, K. Okay, so x, y, z, I, J, K. Yeah, and then you can so usually in literature, usually, right? So there could be exception, but usually we write down I is 1 0, and then J is 1 0 0, because it's three-dimensional, right? And then J is 0 0 1, and then K is 0 1 0, okay, and then K is 0 0 1, okay. Yeah, and then the proof, I think we're fine, because we talked about that, right? The inner product with itself is just norm times norm. Yeah, all right, and then and then because the coordinate vectors, we assume that they are orthogonal to each other, meaning that perpendicular, like their angles are 90 degrees to each other, so that's why, like here, I inner product with J 0, J inner product with K 0, K inner product with I is 0, right? So the reason is just here is actually plugging the inner product formula here, like inner product of I times J is the length of I times the length of J, and then times the cosine 90 degree, okay? Cosine 90 degree. Right. And then, okay, so dot product for algebraic vectors, we also we also talk about this formula in here, right? So it's given by this. So look at this. So for the x, again, like inner product is a scalar, like just times the x scalar ax times bx, and then ay times by, and then finally z times az, right here and there. So provided like your dimension is 3, see if you have the third z coordinate, right? So exactly like we mentioned first, right? So if u is a vector of component form, x1 y1 is z1, and then v is another vector of component form s2 y2 z2, and then the formula is just multiply the x together and multiply the y together and multiply the z together. Okay, so this is nothing too fancy about what we talk about, right? So we can maybe calculate this a inner product b and just multiply them together. So this 1 times 0 here, and then plus -2 times -1, and then plus 0 times 2, right? So this become 2. Okay, and then if you see like the IJK form here, I think it might be convenient just to convenient to put it in component form so that it's easier to multiply together, right? So this IJK, so I just write down the parameter of the scalar 1 here, and then in front of J is -2 here, and then in front of K is -1 here. So and then so A in front of I scalar is -1, in front of J scalar is 2, and there's nothing in front of K, so it's 0, right? And then you also multiply it just like what we plug in the inner product formula before. Okay, and then here is also so -1, and then 2, and then -2. Okay, so so I can write down maybe for the second one b. If you want to see it, just -1, 1, and then plus 2 times -2, the y scalars, and then the z scalars, 0 times -1. Okay, and then angle between them. We also talk about this here previously, right? It's exactly the same formula. You don't need to remember new ones, right? It's just our AB inner product is normal, or the length of A times the length of B times cosine theta. So cosine theta is this over this. But again, the only thing to note that when you plug in, you might sometimes I think we did a question that the inner product AB is directly given, right? So, but however, it might not happen that the inner product value is given to you, so that you need to calculate yourself. So ax bx plus ay by plus az bz, right? And then these two are the norm of A and norm B, right? And here it's just giving you some value for cosine theta. If AB are parallel, the same direction, cosine theta is 1, because theta is 0, right? Because in this way, theta is 0. So cosine 0 is 1, right? And then this is theta is 180. And then so cosine theta 180 is -1, right? And there's also talk about when theta is 90 degree. At the bottom here, that cosine 90 degree is 0. Okay, so this is the same old thing. So find the angle. So let's do 1. Let's do B. Okay. So let's try. I think it's always convenient to write them down in a component form, just easier for calculation, right? So, and then if I write down, so if I write down the A, I can just say like I, J, K component, right? And then I just put it in the scalar in front of the I, J, and K, right? Right? And here I just put it down -1 and 0 and -2 here. Okay. And then B is I'll just write it down. So again, I put it down IJK and then just put it down there scalar, right? So I0, J -2, K1. Okay. And then so find the angle, cosine theta is the same old trick, nothing new, right? So I think this is like the I don't know, the third time I've written it down. So I think it can be easy for you guys, right? So here is 0 times -1 plus 0 times -2 minus 2. Okay, and then the length is of course square root of 1 squared plus 2 squared, and this is square root 2 squared plus 1 squared, and then you just calculate this, right? So this shouldn't be this should be like easy breezy, okay? And then find a non-zero vector perpendicular to each of the vector. Actually, this one you can directly use cross product, okay? But I don't know if there is going to talk about cross product here, but yeah, so can use cross product, okay? But however, we're just talking about inner product, so I guess I'll just write it down. U is equal to x, y, z, so that set up two relation U inner product with A is equal to 0, and then U inner product with B is 0. And then you just plug it in, right? Plug it in so that, let's see, A is this, so x plus 5y, and then minus z, right? And then this is u in a product b with -3x, and then plus y, and then plus 2z. And then you might have the question now, we have two equations but three variables. What are we going to do? But that's okay, because you don't need to solve for like an exact answer, like the only one answer. You just solve for the relationship between x, y, z, and then you just pick a number. Like there could be like a relation, and then you just pick a number, right? Yeah, so yeah, maybe I can demo a little bit, and then maybe using the first one, like you can get like z is equal to x plus 5y, right? And then 1 to 2, yeah, you just simplify these relations, right? And then 2 is -3x plus y plus 2z. I just plug in this relation here. X plus 5y is equal to 0. Okay. And so I get a relation after two equations for three variables. We can only solve reduce like 2 degree of freedom, like meaning reduce like 2 free variables, but still, okay, you'll see. So z is equal to x plus 5y, right? And then I plug in the z here, right? And then I get another relation for x, y. So this is becomes negative 3x plus y plus 2x plus 10y and equal to 0, so that we can have negative x negative x is equal to minus 11y. Okay, so x is equal to 11y, right? So x is equal to 11y now, and couple with, so y is equal to y itself, right? And then this is quite important actually, to solve for x, y, z. If you have a free variable, meaning that like 3 variables, you can only like fix the exact relation of 2 of them, but then like 1 variable is still free, like unknown. Like variable means it can take like random values, or like all the values varying in the coordinate system, right? So x equal to 11y, y is equal to y itself, and then z is equal to x plus 5y, means, so x is 11y, and then plus 5y is 16y. Okay, so that this is quite important actually. This is standard, the steps that you go learn linear algebra, and then you have 1 degree of freedom, but then like you solve for a system of vectors, or like a set of vectors, and then you can pick one specific, right? So because remember that in the beginning we assumed that u is equal to x, y, z, so u now is equal to x, y, z, and then we can plug in 11y, y, and then 16y, and then y is our free variable, so y free variable, y is in R, so you can pick anything now. So can pick free variable y to be any specific value, okay? To be any specific values. Yeah, and then just pick one. You're fine, okay? And this is what I mean. You have 1 degree of freedom, because instead of solving like a exact value, like a known value for x, y, z, but you one value for y, but you solve for x, y, z in terms of a free variable y, 11y, y, and 16y. So this is actually the answer for you, the solution set. It's not a specific solution, but a solution set of u, right? This is solution set just because y is in R. Okay, so this is like you use it over and over again in future in your linear algebra step. You have 1 degree of freedom, like a free variable. Okay. Yeah, but to solve this question is easy, right? So the idea of this question is easy. Okay. The idea of this question is just 2 vectors perpendicular to each other. You just say, oh, inner product is 0. Okay. Let's see the last one. Find the angles. Okay. 3 points. Yeah. So now I think the it's the same trick, because the content of this PDF not that much, and I think we just like calculate the get AB is equal to the coordinate of B minus the coordinate A, like 0, 1, 2, we can get AB is equal to 1, the minus 1, 0. Okay, and then similarly, you got like BC, and then got also like AC, for example, and then find the angles. But of course, be careful with the how to say the direction. Okay, be careful with the direction. Yeah. So maybe I should say BA. Okay, maybe I should say BA. So cosine theta is you know maybe like BA vector, I should say this. BA, inner product, okay, inner product. I don't know why inner product, and then BC, and then the norm, okay? Yeah, so this is nothing fancy. I think it's just using over and over again, okay? And then so find the angles, and also find the angles between vectors and the coordinate axis. Yeah, again, this is nothing but inner product, using inner product again, right? So, and I also think it's convenient to write it down with component for -2, 1, 3, and coordinate axis. Yeah, coordinate axis, you can just say, oh, I is equal to 1, 0, 0, the same matrix, J is equal to 0, 1, 0, K is equal to 0, 0, 1, and then so the angle theta cosine theta, the angle between A and I is just A inner product with I with the length, right? The length of I is equal to 1, right? And then you just this is plugging in, right? So this is -2 times 1, and then plus 0, 1 times 0, 1 times 0, right? Plus 3 times 0, and 0. And then the length of A is square root, right? This 2 square, 1 square, 3 square, and then times 1, right? So the length of I is 1. Yeah. Yeah. So I think these are, yeah, you guys should be fine with this. This is perpendicular. So are they perpendicular? So equivalent to checking if they're inner product. So this is important. Just to remember, perpendicular is equivalent with inner product with 0, right? So when you see perpendicular, you just immediately flash it in your mind. Oh, inner product, is it 0 or not? Right? So check, is it 0 or not? So check if so this is like 2k, and then plus -2 times 2k minus 6, and then plus 3 times 6. I don't know if this is okay. To find values of k, right? So solve for k, yeah. So you just simplify this so that 0 become like, I guess this is like -2k after simplification, plus 12 plus 18. 12 plus 18 is 30. Okay, so k is equal to 15. Yeah, something like that, right? And parallel collinear, okay, parallel collinear. Yeah, parallel collinear is just the cosine theta is equal to 1, or cosine theta is equal to 0. And then it's the same old trick, you let A in the product with B, and then over the norm A and the norm B. Okay, I think we're pretty good for now. Good shape for now. Oh, okay, parallel. Sorry. Parallel means 0. Cosine theta is 0. Okay, and then I should move this down, right? Okay, so we'll stop here for now. Okay, stop this.